Well, what do you know? A video that isn't a brief history or an iceberg. Well, more or less. Today I'd like to talk about cancelled spaceflight projects, as many as possible and not in a specific order, but I would like to lift a page from the iceberg format and do them in descending order of obscurity. This doesn't really mean much as far as higher tiers go. The general public doesn't really know about any of these. A hard-to-swallow pill for spaceflight fans is that the general public knows roughly the following about spaceflight. NASA landed on the moon once, there's a space shuttle, many don't know it was cancelled, SpaceX blows everything up, and the Russians have that one thing that they don't know is called Soyuz. So pretty much everything we'll discuss today is obscure to the public, but I'll try to do it in the order that spaceflight fans are most likely to know about them. Another thing to note, what is a cancelled space project? Well, this will also affect the order they're discussed in. Some projects are planned, approved, started, and maybe even operate for a little while before being cancelled. Others are cancelled before they fly. Others are never even approved in the first place. Additionally, I won't consider things like the space shuttle to be cancelled. Retired is more appropriate given that a 1970 spaceplane probably shouldn't have flown all the way to 2011 anyway. Buran, however, that was absolutely cancelled. Let's get started. Speaking of, Buran is one of those things you learn about pretty quickly once you start digging into spaceflight. Since the shuttle flew for 30 years, it dominates the memory of post-Apollo spaceflight, and it isn't long before somewhere you read, "Did you know that the Soviets had one too?" Well, they did. Sort of. It was developed from 1980 to 1988, flew once, and then was cancelled. Just looking at it, you can see that it took some obvious inspiration. There are those who would try and tell you otherwise, but the truth is that Buran was the direct result of industrial espionage and government paranoia. Soviet military officials used the US space shuttle as a weapon against Soviet politicians. The General Secretary of the Union, Leonid Brezhnev, was convinced that, quote, "that damned shuttle could zoom down on Moscow at any minute, bomb it to smithereens, and fly away." This of course wasn't true. The shuttle wasn't capable of powered flight in the atmosphere after its launch, and with its poor glide ratio, wouldn't make a very good single-run bomber anyway, especially since it lacked bottom-side doors. Nevertheless, Brezhnev was convinced to approve the design of a, quote, "alternative weapon" in the form of Buran. Officially signed into motion in 1976, 1 year before the NASA shuttle flew in-atmosphere glide tests, the Soviets needed to play catch-up and fast. NASA had been working on various spaceplane concepts for some time now, some of which we'll come back to, but the Soviets had only one, called Spiral, which by now was 13 years out of date. They had one advantage though. NASA's space program, unlike the Soviets, was public. They were keeping no secrets, but the Soviets still had to spend significant amounts of time and resources on gathering together databases of information on shuttle blueprints that they took off of public data networks and parsing out their own design based on that. The result was two separate systems. Buran was the spaceplane, obviously heavily based on the US shuttle orbiter, and the other was Energia, Buran's launch system, designed to be able to carry other payloads outside of the spaceplane. Because its initial purpose was to fly Buran, these other payloads would be similarly side-mounted to the launch system. Obviously visually similar to the US shuttle, Energia utilized a liquid hydrogen-fueled core stage with 4 RD-0120 engines, roughly equivalent to NASA's Space Shuttle main engine. However, unlike the NASA shuttle, these were not reused, which was considered to be acceptable in exchange for a launch system not restricted to only Buran. In place of NASA's twin solid-fuel boosters, Energia used 4 Zenit boosters, fueled by RP-1 and utilizing the powerful RD-170 engine. Before we get to the operational history, I'm going to talk very briefly about Buran's reputation. There are those out there who would try and tell you that Buran was better than the NASA space shuttle, and this simply isn't true. To quote a more extensive video about the downsides of Buran,
"One was designed for the betterment of humanity, the other one is Buran."
Aside from it being largely a fear-based military response to a vehicle that had pretty limited military capabilities, outside of stealing spy satellites, which it never got to do, its proposed design changes that are touted as better are dubious at best. One of the main things people will often point to is its use of liquid fuel rather than solid fuel for the boosters. However, while it's true that solid fuel boosters generally cannot be shut down after they're lit, there are some exceptions to this, they're not particularly dangerous. The loss of Shuttle Challenger came from utilizing the SRBs outside of their design parameters in weather too cold for the extrusion process of the O-rings to be effective at sealing casing gaps. Furthermore, we have to consider possibilities. If an anomaly appeared in a booster and it were to be shut down prematurely, Would that matter? At liftoff, the shuttle's SRBs were providing around 70% of the thrust of the entire launch system. If one of them shuts down, the shuttle plummets, and Buran didn't have a launch escape system either. Buran was tested extensively with numerous in-atmosphere models, including one that utilized 4 jet engines to allow it to take off and land without the assistance of a carrier aircraft. And to go back to how terrible the shuttle's glide ratio was, take a look at this photo. You may notice that when the NASA shuttle lands, its nose points downward, with its forward gear being slightly shorter than the mains. This Buran test analog, however, had an extended forward gear because it needed to obtain an absurdly high angle of attack to generate enough lift to fly on its own. They really did fly like bricks. Energia flew once without Buran, and I'm really only bringing this up because I find it, quite frankly, hilarious. The Polyus spacecraft, a prototype orbital weapons platform intended to destroy anti-nuclear satellites, thankfully never ended up in orbit, nor did the satellites it was designed to shoot down. It was mounted upside down on the Energia launch system, intending to turn 180 degrees and fire its engine to complete orbital insertion. However, after Energia performed perfectly on its debut flight, Polyus proceeded to separate from it, turn 180 degrees, then turn 180 more degrees, returning to its original backward orientation, and fired its engine. A faulty inertial guidance system caused it to put itself into the South Pacific Ocean thanks to a rushed production schedule that skipped one too many tests. That's what you get for violating the 1967 Outer Space Treaty. Energia's second and final launch would take Buran to orbit with it, specifically the OK-101 model, specifically intended for orbital flight unlike its in-atmosphere test craft. It was launched without crew, with some sources saying it wasn't even capable of carrying crew at the time, lacking a life support system, and successfully reached orbit on November 15, 1988. It completed 2 circles around the Earth, fired its orbital maneuvering engines to descend into the atmosphere, and returned to the launch site for an automated landing 206 minutes after liftoff. Examination after the fact revealed 8 of its thermal protection tiles were missing, including several off the top of the cabin, the body flap, the vertical stabilizer and rudder, and the left wing, a critical area as NASA knows from experience. Would it have flown again? Who knows, because the program was cancelled amid the Soviet budgetary crisis that preceded the collapse of the Union. 2 test orbiters remain rusting away in storage, and the jet-equipped orbiter is on display in a German museum, but this first flown Buran would meet its demise in 2002 alongside another test article when its hangar collapsed onto it in an accident that claimed several workers' lives. Now, while we're on the subject of space shuttles, let's turn to what the NASA Space Shuttle could have been by examining early cancelled proposals for its design. Technically, I should begin this by talking about the Apollo Applications Program, but we'll circle back to that. Instead, we'll start by talking about the Integrated Program Plan, or IPP, which would eventually evolve into just the Shuttle program. In February of 1969, NASA's Space Task Group was given the job of proposing human space projects beyond Apollo. By September, the task group had responded with several proposals that outlined the IPP. They suggested a permanent space station module in low Earth orbit, with plans to expand it with more modules, as well as a possible lunar orbit station as well. The ambitious plan envisioned a station capable of holding 50 to 100 people, not quite the 6 to 12-ish we ended up with on the ISS. It also included a space tug, something similar to but much more larger and capable than Cygnus, that could be used to move both crew and equipment, even making it adaptable as a lunar lander, as well as a nuclear-powered vehicle capable of sending crew and supplies interplanetary. We'll come back to that. And finally, a shuttle for sending crew to Earth orbit. However, once political support for space programs began to wane after the first Apollo landing, Nixon realized Congress wasn't going to support these lofty plans and rejected all of them except for the space shuttle. As a result, Thomas Paine, the NASA administrator who had been the face of the ambitious IPP, resigned in 1970. Early studies for the space shuttle's design took place the year before Paine's resignation, with the original proposal coming from North American Rockwell. It was a 2-stage delta wing design with a massive flyback booster, on top of which the shuttle orbiter was mounted. Both stages would utilize both jet and rocket engines, with separate fuel and control systems for each mode. The booster would carry the shuttle through part of its launch, much like the SRBs of the final design did, before separating and flying back to a runway, while the shuttle continued into orbit. However, costs for this design quickly mounted. A flyback booster with this kind of lift capability would not only be massive, but very expensive. Supporters argued that enough launches would result in overall lower launch costs eventually through reusability, but this ended up not being enough to influence the final decision. The reusable booster was dropped in favor of a semi-reusable system, partially reusable boosters, and a discarded external fuel tank that would allow for the shuttle itself to have a much larger payload bay. However, before we get to finalizing the design, let's talk about the DC-3. Maxime Fazet, the principal designer of the Mercury spacecraft, attempted to salvage the original dual lifting body design initially proposed. Seeing an unacceptable amount of development risk and never-before-tried methods, he instead proposed the DC-3, which looked much more like a pair of conventional aircraft. Having an almost cylindrical fuselage and short, low-mounted, slightly swept wings, it would re-enter the atmosphere at a 60-degree nose-high angle, presenting a blunt body shape not dissimilar from Mercury to the airflow. Instead of being designed for a better glide ratio, it would instead open ducts and start up jet engines to carry itself to a powered runway landing. The wings were intended to compensate for the complexity of the blended wing design. As development changed the weight and balance of the vehicle, changes to the entire structure of the shuttle would be required to compensate. However, with the DC-3 design, these weight and balance changes could be addressed simply by moving or reshaping the wings, leaving the rest of the craft relatively the same. However, after Thomas Paine resigned, his replacement, James Fletcher, ordered reviews of the space shuttle concept. Hoping to shore up support for the program, he pitched the idea of using it to support Air Force requirements, such as launching a series of large spy satellites into polar orbits. This put further constraints on the vehicle's required abilities, including a cross-range capability of 1,500 miles or 2,400 kilometers, born of a desire to be able to land again after a single orbit, the so-called once-around. However, the DC-3 was designed to be a largely ballistic re-entry, incapable of being significantly altered by the use of the wings. It simply wouldn't be able to achieve these kinds of cross-range capabilities, and thus was cancelled in favor of the Class 2 design with external tankage. Ironically, the final shuttle would never make polar launches anyway, since the plans for these, done from Vandenberg in California, would be cancelled following the Challenger disaster. Involvement of the Air Force would end up being a significant factor in the shuttle's final design. The program had limited support and funding, and the Air Force already had two of its major space projects cancelled, which we'll come back to, leading to a major need to demonstrate the ability for cooperation between NASA and the military. The National Reconnaissance Office requested an expansion of the proposed payload bay size, expecting future spy satellites to become larger. The Air Force effectively also gained use of one of the orbiters at no cost, since they didn't pay for the development or construction. Shuttle Discovery, intended to fly the first West Coast mission, was earmarked as the dedicated U.S. Air Force shuttle. All of this potential military use for the shuttle led to the decision not to cancel it in 1979, when it was already well behind schedule and over budget. However, those two factors did lead to simplifying and cheapening the final design. Liquid-fueled boosters would have provided better performance, less environmental impact, and less risky development, but solid-fueled boosters were cheap and easy. By 1972, contracts had been signed for the construction of its final design, giving us the heavily crippled shuttle we know to have existed in reality, flying its first flight almost a decade later in 1981. Before we move on from shuttle stuff, and before it inevitably comes back somewhere else in this video, let's talk about Shuttle-C, which is this thing. Yes, I know it looks kind of goofy, like someone strapped a half-finished shuttle orbiter to the side of the launch stack, and that's kind of what it is. This proposal was first thought up around 1984, endeavoring to cut down on costs for a heavy-lift vehicle by reusing technology and hardware from the shuttle program. The idea was to remove the crew and reuse requirements and turn the shuttle into a single-use cargo vehicle. Following the Challenger disaster, it became clear that NASA's intended launch rate of 2 shuttle flights per month was not going to be feasible. Shuttle-C was proposed to compensate for this because it stripped away a large portion of pre-flight and post-flight processing. When there's no crew aboard, safety becomes a slightly smaller concern. When the vehicle isn't intending to land, you don't need to make sure it'll be able to. Shuttle-C even went far enough in development that a full-scale mock-up was put together at Marshall, and there was even an early 1990s plan to use 6 Shuttle-C launches to assemble a Mars spacecraft in Earth orbit. However, once the shuttle was slated for retirement, so was Shuttle-C. Now, let's go back in time a little further to what led to NASA to develop the IPP in the first place, the Apollo Applications Program, or AAP. The thing about Apollo is, boy, I feel like I've said that before, well before the program was completed, hardware development would have already been completed. A total of 15 Saturn V rockets were constructed, 2 of which never even flew, with the last SA-515 being assembled and tested in 1970. A lot of time, money, and infrastructure had been built up to support Project Apollo, and at the rate things were going, it was all going to be cast aside in favor of new, smaller projects. However, Wernher von Braun and the Marshall Space Flight Center had created a lot of engineering jobs for Saturn V production, and so the world's least controversial German rocket scientist came up with a plan. The AAP was essentially a last-ditch effort by von Braun and co. to come up with new ways to utilize the hardware they had worked so hard on, keeping people employed and keeping production going. There were several ideas, the simplest and most immediate being Apollo Extension Series or AES lunar bases. Since one post-Apollo proposal considered extended lunar programs with long-duration stays, one AAP concept was to land a shelter based on the Apollo CSM on the Moon, at which point a two-person excursion team would land in a separate Apollo LEM to occupy it for up to 200 days. They would make use of a rover and a manned lunar flyer, as well as possibly be delivered logistics vehicles that can construct larger, more permanent shelters. The AAP also explored Earth-orbiting space stations. Well before Apollo, von Braun had an ambitious plan for a massive wheel-shaped station that would spin for artificial gravity and facilitate missions to Mars, but this was widely rejected. Instead, von Braun proposed what would eventually become Skylab, a single-module research station constructed out of a spent upper stage of the Saturn V. His proposal utilized the S2 stage, which would be used as a rocket to reach orbit, and once there, be drained of remaining propellant and converted into a functioning workshop while in space. This was then scaled back to do the same with an S4B, the third stage of the Saturn V, and then scaled back even further to fully convert the stage into a dry workshop, ready for use as soon as it reached orbit, having never contained propellant or engines. Another AAP proposal was the Voyager program. No, not that Voyager program, but the Voyager Mars program. This intended to use uncrewed landers derived from the Apollo Command Module, launched on a Saturn 1B rocket with a Centaur upper stage. With early Mariner discoveries of the nature of Mars's atmosphere, the design was changed to utilize both an orbiter and a lander, necessitating the use of the Saturn V for the larger payload, which I assume von Braun was very happy about. A few other AAP proposals were considered, including a solar observation telescope based on a modified LEM ascent stage, as well as a similar Earth observing module. However, easily the wackiest idea to come out of the AAP was the manned Venus flyby, and before I explain what that was, I'm just going to say it. This is one of the dumbest, most pointless, and most dangerous spaceflight proposals ever made. The manned Venus flyby proposed sending 3 astronauts on a flyby mission to Venus using an Apollo-derived spacecraft that consisted of linking a CSM with an S4B wet workshop, similar to the early Skylab proposal. The stage would be filled with living quarters and needed equipment that could withstand being immersed in fuel, with more sensitive equipment placed in the interstage between the top of the tank and the CSM, a space normally reserved for the Apollo lunar module. To save space, the sizable bell nozzle of the CSM engine would be removed, replaced with 2 smaller engines used on the lunar module, able to be kept within the service module's bottom rather than extending out past it. One of the more amusing aspects of the mission's profile is that the CSM would perform transposition and docking, that is, separating from the S4B, turning around, and then docking to it, before the burn to leave Earth orbit was performed, unlike on Apollo missions where this was done afterwards. What this means is they would be facing toward the rear of the craft when it made its burn toward Venus, and instead of being pushed back in their seats, they would be pushed forward, referred to as eyeballs out. The purpose of the mission would be to measure the various properties of Venus with radio and radar astronomy, spectroscopy, and more, and here is where my personal issue with the mission comes in. Every single piece of data that can be acquired by flying past Venus can be acquired with uncrewed instruments. There's absolutely no need for a person to be there. The only thing the astronauts get out of the trip would be a close-up look at Venus, which, by the way, isn't all that impressive. The planet is covered in thick, dense cloud layers that completely obscure the surface, and even those clouds aren't particularly pretty. We're used to seeing images of Venus taken in ultraviolet or using false colors, but the truth of Venus is that it looks like this. It's not particularly impressive visually. This, combined with the risks of the mission, 2 full years in deep space, no way to return easily, is extremely risky with Apollo-era technology. Consider that Apollo 13 barely made it home, and it was only going to the moon. This mission would be going over 100 times further away, and it wouldn't even have a lunar module as a lifeboat. If that wet workshop broke down, those guys are not staying alive trapped in a CSM for an entire year or more. The Apollo Applications program was kinda insane. Now let's pivot and go in a completely different but still somewhat insane direction. Project Orion. We can argue all day about which rocket fuel is most efficient, Hydrolox, Kerolox, Methalox, but none of them compare to exploding a nuclear bomb behind your spacecraft to push it forward. That's the basis for Project Orion. In 1946, nuclear energy was a brand new technology that set minds alight with the possibilities that could come from such high-energy reactions. Stanislaw Ulam, a Polish scientist, made use of his experience with the Manhattan Nuclear Project, concocting an idea inspired by a science fiction concept written by Robert Heinlein. He proposed a concept he called nuclear pulse propulsion, making preliminary calculations in a Los Alamos memorandum with American physicist Frederick Rains. In 1955, Ulam co-authored a classified paper that went into more detail using nuclear fission bombs, quote, ejected and detonated at a considerable distance for propelling a spacecraft at incredible speeds. Joining the growing project would be Ted Taylor from General Atomics and physicist Freeman Dyson, and by 1958, Project Orion was sponsored by ARPA at an initial level of $1 million per year. They would withdraw support in 1959, but more would come from the US Air Force with the condition that Orion eventually find a military use, as well as some support from the NASA Office of Manned Spaceflight. The biggest bit of actual hardware was testing of a model blast shield and shock absorber designed to convert the detonations into usable energy while also keeping the crew and equipment safe from harm. The scale model obviously didn't use nuclear explosions, instead chemical explosions scaled to be equivalent in power with the model. In November of 1959, it performed its most successful test, propelling the test article 100 meters into the air with a series of 6 detonations. Around this time, NASA also produced a profile for a crewed mission to Mars that would take only 125 days to send astronauts on a round trip. In 1963, the United States signed the Partial Test Ban Treaty, which prohibited any detonations of nuclear weapons anywhere except underground, making Orion effectively impossible. Orion would be cancelled in the next year, and it's a real shame too. Basic Orion designs could create thrust efficiency in the range of 13 times more effective than the Space Shuttle main engine firing at full blast in the vacuum of space. Further refinement of the design estimated thrusts in the millions of tons. For reference, the Rocketdyne F1 engine on the Saturn V produced around 680 tons. Its biggest problem related to weight restrictions, as with many things spaceflight related. The smallest practical vehicle was determined by the smallest achievable bomb yield, making the smallest possible vehicles only large enough to be used as orbital test vehicles, while still being in excess of 800 tons in mass. Because of this, a lot of effort was put into researching much larger vehicles, the biggest of which was known as the Super Orion. With a diameter of over 400 meters, over 1,000 bombs weighing 3,000 tons each, and a total mass of around 8 million tons. Effectively the size of an entire city, my question becomes, how do you even get something like that up into the air in the first place? I don't know, but Hayes Grey Art created this simulation, which features a host of absolutely gigantic solid boosters, some of which drop off less than a minute into the flight, and this really seems like the only way to effectively do it. Just daisy chain as many boosters as humanly possible in the most Kerbal Space Program design possible until it reaches the upper atmosphere before engaging the Orion drive. Freeman Dyson analyzed the possibility of Orion being used for interstellar travel in 1968 with 2 designs to perform a flyby of Alpha Centauri, our nearest solar neighbor about 4.24 light-years away. Both options would either have to be uncrewed or be some kind of self-sustaining colony ship that holds multiple generations of crew members. Option A, the energy-limited Orion, was a very, very large vehicle that would accelerate for 100 years at such a pace that nobody would even feel it, eventually reaching 1,000 kilometers a second and flying past Alpha Centauri after 1,330 years at a cost of $3.6 trillion. I'm convinced that this option only existed purely to make the second option, the momentum-limited Orion, seem more feasible. Being only a fraction of the size, this one was capable of reaching 10,000 kilometers a second, just over 3% the speed of light, by accelerating at 1g for 10 days and would reach Alpha Centauri in 133 years at a cost of $0.3 trillion. Again, bear in mind that both of these options would fly past Alpha Centauri without the possibility of slowing down, which would need to be achieved by facing the other way and dropping an equal amount of bombs, merely continuing into deep space indefinitely after a quick pass through another solar system. Many of the problems with Orion are quite obvious. The consequences of multiple nuclear detonations above the atmosphere aren't exactly predictable. Oh, but it's space, it's mostly empty, isn't it, you might say. and you'd be right except for the existence of solar winds. Making the space around us even more irradiated than it already is could have some pretty rough consequences in the future, but it's pretty hard to say with the limited amount of research done into the subject. Other problems with Orion aren't as readily apparent. Consider the strain put onto the pusher plate after being subjected to dozens if not hundreds of nuclear explosions. There was a lot of focus put into material studies that tried to figure out the best way to keep the plate from being eroded away by radiation and the force of the explosions. Steel was considered the best material, ablating by less than 1 mm without any protection. However, it was discovered that by spraying it with an oil would cause it to not ablate at all. Oddly enough, this was discovered by accident. A test plate with oily fingerprints was discovered after the fact to have suffered no ablation where the prints were. However, at the time, proper testing of the turbulence created by explosions on the pusher plate was simply not possible without actually detonating a nuclear explosive near a test plate. Of course, now modern computer simulations make this point moot, but by the time that was available, Orion was long dead. There have been similar studies to Orion conducted over the years, such as Project Daedalus in the 1970s. Conceived by the British Interplanetary Society, this was a probe intended to reach Barnard's star, 5.9 light-years away, in around 50 years. Instead of nuclear pulse propulsion, it would utilize a fusion rocket engine consuming pellets of deuterium and helium-3, igniting in a reaction chamber via electron beams. As helium-3 is not an abundant material on Earth, the plan was actually to harvest them from the atmosphere of Jupiter with hot air balloon-supported robotic factories. My favorite part of Project Daedalus is that the entire point was to keep the design to, quote, existing or near future technology. While we're talking about concepts that are big in scale, we might as well cover Sea Dragon. Formerly a little more obscure, interest in it has been revitalized when it was featured in the Apple TV Plus series For All Mankind, used to resupply an expansive lunar base. Designed by Robert Truax of Aerojet in 1962, the idea was a low-cost but heavy-lift launcher, a concept now called the Big Dumb Booster. Low-tech but high-power, BDBs were considered far cheaper to operate despite not being particularly efficient in design, with this being offset by their high payload capacity. Sea Dragon was one such rocket, being a staggering 490 feet in height, over 100 feet taller than the Saturn V, and with a mass of 39 million pounds, it was to be launched from the ocean to keep the cost of ground support equipment low. It would be towed to the launch site horizontally, after which a ballast system attached to the bottom would hoist it vertical, with the payload at the top of the second stage just above the waterline for accessibility. The ballast system would be released when the first stage, an extremely powerful single Carolox engine, ignited and carried the rocket out of the water and up to around 40 kilometers in altitude. The second stage, also a single engine, would burn hydrolox for 260 seconds until it was in orbit. Everything about Sea Dragon was about simplicity and low cost, constructed out of steel sheeting at a seaside shipbuilder and with design elements for partial reusability of the two stages. It would theoretically have enough capacity to launch the entire ISS in a single launch, some assembly required, of course. While NASA and Todd Shipyards expressed some interest in Sea Dragon, neither would pick it up, and while Space Technologies Laboratories conducted a program review, budget pressures led to them closing their future projects branch and effectively ending the possibility of Sea Dragon ever leaving paper. Continuing with the concept of big dumb boosters, let's take a look at Otrag. Otrag? O-T-R-A-G? I don't know, it's German. Scott Manley, how do I pronounce this?
Otrag. Orbital Transport und Raketen AG, or Orbital Transport and Rockets Incorporated.
Otrag, got it. Thanks, Scott. Founded in the early 1970s, Otrag was actually the very first producer of commercial space launch vehicles, an industry now filled with big-name players such as SpaceX, Rocket Lab, Blue Origin, Firefly Aerospace, and many more. In the wake of Project Apollo, the potential gains of space exploration stood in direct contrast to the immense costs of the lunar program, and there was a lot of demand for the study of making going to space a lot cheaper. German aerospace engineer Lutz Kaiser founded Otrag and won a contract from the German Ministry of Science and Technology for demonstration of a cheap launch vehicle technology orders of magnitude cheaper than existing rockets. Enter the Otrag rocket. The premise is simple. Mass-produce clusters of small, cheap, pressure-fed liquid propellant rockets that can be arranged together in stages, increasing their size as needed by the intended payload. The individual rockets would be simple and easy to produce in large quantities, bringing down overall costs of launches. This caused many ripples in the young pond that was the aerospace industry, with established launch providers already being accustomed to a low competition market of guaranteed profits through high-cost fixed-fee government contracts. On the other hand, the potential benefits of the project attracted the involvement of some big names, namely former director of the Marshall Space Flight Center and pioneering designer of the Saturn V, Wernher von Braun, as well as Kurt Debus, former director of the Kennedy Space Center, who both signed onto the team after they retired from NASA. It was actually von Braun who suggested the concept of parallel clustering the tanks and engines, taken from his previous design of the Saturn I, which clustered together 8 Redstone tanks and a single Jupiter tank in the middle. However, both von Braun and Debus got nervous when Kaiser made the decision to flight test Otrag in developing countries, building a padding gantry in Shaba in the Congo. They became concerned about the possibility of the technology being misused for weapons, something both Debus and von Braun had extensive experience with. Testing activities made large powers anxious. The USSR and France both didn't want to see Germany achieve an indigenous launch capability, perhaps remembering the Nazi regime's V-2 missile bombing campaign, whoever designed that thing, and both countries began a propaganda campaign against Otrag. The USSR disseminated misinformation that alleged Otrag to be a cover-up for German and South African cruise missile development, which was picked up and given credibility by American mainstream media. Pressure from the Russians convinced the Congolese government to withdraw permission to use their launch site, and Otrag left in 1979. At the same time, further pressure from the Soviet and French presidents on the German government forced them to terminate Otrag development in Germany, and the project moved its tooling, materials, and a new test site to a remote area in the desert in Libya in 1981. The tests went well, launching 4-module and single-module vehicles until a 100% qualification of the technology and confirmation of the extremely low production and launch cost. However, the final blow came after Germany became party to the Missile Control Regime, a multi-country agreement that attempts to limit missile development, one aspect of which prohibits testing in developing countries. In 1983, before Otrag could move everything to Sweden as planned, the Libyan government unlawfully confiscated all of Otrag's manufacturing and test equipment. However, without any know-how or blueprints that Kaiser managed to retain, they only managed a few test launches with mixed results before they abandoned it. At this point, Kaiser gave up in the face of constant political pressure, and after dumping $200 million into his project, he shut down Otrag in 1987. It never saw a staged test launch and never reached its intended potential, despite everything on the tech side going more or less according to plan. At this point, obscurity becomes pretty relative, so I'm going to start more or less picking them at random. Remember Skylab? Well, if you don't, I'm not going to repeat myself too much because I already made this video. Check the top right corner. Skylab, converted into a research laboratory out of a Saturn V third stage, had a backup unit, Skylab B. Built in 1970 by McDonnell Douglas as part of the yet-to-be-gutted Apollo Applications program, Skylab B had a few proposed uses, the most popular being an extension of the Apollo-Soyuz test project in 1975. Initially limited to a week-long mission between a Soviet Soyuz and an Apollo CSM, launching Skylab B aboard the Saturn V that had been intended for Apollo 20 could have turned Apollo-Soyuz into a 3-month mission. Further proposals included an advanced or international Skylab, necessitating a second workshop module to be launched by the other remaining Saturn V, with the 2 connected modules being serviced by Apollo and Soyuz spacecraft, and eventually the Space Shuttle. The initial hope had been for the shuttle to be active before the first Skylab was retired, but development fell behind hard in the face of diminishing budgets and design difficulties. One other idea that was talked about but never truly considered was Skylab Salyut, combining Skylab B with a Soviet Salyut station. However, this presents a lot of difficulties. Docking adapter confusion is one thing and solved relatively easily, consider the androgynous system adopted for Apollo-Soyuz. However, the atmospheres of the 2 stations didn't match. Both used a nitrogen-oxygen mix, but at different pressures, with Salyut close to sea level pressure but Skylab much lower, around 5 psi. Either the 2 nations would have to agree on a standard pressurization system, which would likely require alteration of the one that didn't match, or they would require an airlock and lengthy pre-breathing procedures before moving from one workshop to the other, which would not only be impractical but possibly unsafe in the case of an emergency. Of course, Skylab Salyut is a neat idea, but difficult, costly, and never seriously considered. Since we've started talking about Soviet stuff, now is a good time to cover a few of those subjects. Let's start with the big boy, N1. I've talked about it before and it's got enough details to maybe merit its own video one day, but today we'll just cover the basics. The N1 was the Soviet answer to the NASA Saturn V, a monstrous super heavy lift vehicle intended to send crews to the moon. While undeniably powerful and impressive, N1 was unfortunately doomed to fail due to the circumstances under which it was developed. With development officially starting in 1965, just 2 years before the Saturn V made its debut flight, the N1 was underfunded and rushed, and badly derailed when its chief designer, Sergei Korolev, passed away just a year later. Most of the problems centered around its incredibly complex 30-engine first stage, which had a fuel and oxidizer system that would make an IT professional blush remembering his least graceful cable management systems. This was effectively what led to its demise. The NK-15 engines on the first stage used a number of valves that were activated by one-time use pyrotechnics, unable to be closed again once opened. This made it impossible to perform static test fires of complete units of engines. Only individual engines could be tested. Sergei Khrushchev would later indicate that only 2 out of every batch of 6 was tested, and those 2 wouldn't be used in a booster. Because of this, virtually every one of the N1's 4 flights would end in failure when destructive vibrations during launch would rip apart turbines and propellant lines, causing fires, cascading shutdowns, and uncontrolled rolling. I won't go over all 4 failures, but one is worth talking about. The second flight, N1-5L, carrying a Zond spacecraft intended for lunar orbit. It didn't last long. After just barely clearing the tower, there was a bright flash of light followed by falling debris, and every single engine save for one immediately shut down. The launch escape system ignited, and the almost fully fueled rocket fell, tilted from the remaining engine's thrust, and slammed down back into the pad. The resultant explosion was, in terms of raw power, the largest accidental rocket explosion in aerospace history, but far from the most deadly. The launch complex was completely leveled with the concrete pad caved in. Shockingly, the vast majority of the propellant hadn't even detonated, with launch crews walking out to the site 30 minutes later to find themselves being rained on by unburnt droplets of fuel. The problem ended up being traced back to an explosion in a turbopump, which created a shockwave that severed propellant lines, leaked fuel, and started fires. The fires burnt through other components that led to cascading shutdowns over a period of around 2 seconds, except for the number 18 engine, which kept firing for a reason that nobody could quite determine. Now, let's dive a little further into the Soviet lunar program, since the N1 had intended to facilitate that eventually. The original plan was a little more ambitious and complicated, and would accomplish everything with a series of Soyuz rockets. Korolyov's design bureau initially put forth the Soyuz ABC circumlunar complex, which would launch 2 vehicles independently and have them rendezvous and dock in Earth orbit before they would then engage in a lunar flyby. At the same time, another bureau proposed a competing flyby mission using a heavy lift rocket that would eventually be dubbed Proton, using the 2-crew LK-1 spacecraft. Not too dissimilar from the NASA Gemini spacecraft, LK-1 would never end up flying, cancelled in favor of the Soyuz 7K-L1, though the same bureau would also first propose a direct descent lunar lander based on this same design, which would also never fly. By the time Apollo was ramping up and making progress, Sergei Korolyov had passed away during surgery in 1966. The Soviets continued development of the Zond program, which would use the previously mentioned 7K-L1 spacecraft. However, they struggled significantly, the first 4 flights failing to complete a lunar flyby. Zond 4 successfully launched into a high elliptical orbit that would have flown it past the moon, but it was launched in the other direction, being a test of spaceworthiness of the Zond capsule. After 2 more failures, Zond 5 would send a handful of organic matter, which included 2 tortoises, on a lunar flyby in September of 1968. Zond 6 repeated the feat in November, but only 1 month later, Apollo would send a human crew into orbit of the moon on Apollo 8. During the Zond program, the Soviets also worked on a landing program, utilizing a similar system to the CSM-LM combo with an orbital Soyuz module and the LK lander, a small single-person craft that was effectively a Soyuz orbital module with a descent engine, ascent engine, and legs. One interesting thing to note is that the landing cosmonaut could not enter the lander via the orbiting spacecraft. He would have to get out and perform a spacewalk to enter the lander, for some reason. Of course, the N1 progress was slow, and its first failures sealed the fate of the program. While the second N1's devastating debris was still being cleaned up, Apollo 11 launched to put an end to the space race. One last Soviet program I'd like to discuss is TKS, the forgotten child of the Union space program. Details are a little fuzzy. TKS was intended to perform resupply flights to the military Almaz space stations, which were cleverly blended together with the Salyut program to put a civilian face on what was essentially a military program. It consisted of 2 parts, the VA spacecraft repurposed from the LK-1 design, and beneath it, the FGB or functional cargo block, which held the supplies to be delivered. The docking unit was placed on the rear at the bottom of the FGB. TKS was intended to be launched either with or without crew, though it only ever flew test flights, the last of which would dock to Salyut 7, the final station in the Salyut program. TKS was cancelled after this, but the remaining finished FGB modules would be repurposed, serving as the basis for 4 different modules of Mir, the previously mentioned Polya spacecraft, and 2 modules of the International Space Station, including its core, Zarya. Let's head back over to the USA for a little bit and talk about possible extensions to their own programs that never got off the ground. More specifically, let's talk about Advanced Gemini and the Manned Orbiting Laboratory. Gemini, being the middle child between Mercury and Apollo, basically meant that it was doomed to live a fast and short existence. Its goals were to master the skills needed for Apollo: spacewalking, rendezvous and docking, and long-duration flights. And Apollo had an end-of-the-decade deadline, so Gemini was born with an expiration date. However, the people behind the hardware that made Gemini happen didn't want that to happen. A series of proposals coming mostly from McDonnell, who built the Gemini spacecraft, and the US Air Force, explored various possibilities to modify and expand the capabilities of Gemini hardware. An early one was the Gemini Ferry, of which there were several variants, intended for sending crew and supplies to various proposed space stations. There were a lot of considerations made, with the biggest focus being minimizing changes to existing Gemini spacecraft. This was hard because while Gemini could dock to a target vehicle, the docking mechanism was too small for a person to squeeze through, making crew transfer only possible via EVA. A different method proposed replacing the existing equipment module with a cargo module that was flush with the base of the craft and docking via a port on the rear of that cargo module. This was fairly unusual, as it would have required remote control of the craft from the station it docks to, which simply hadn't been done before by the US. There was also Big Gemini, also known as the Gemini Transport, intended to take advantage of increasingly large launch vehicles like the Saturn 1B. It was essentially a scaled-up version of Gemini that could provide transport for up to 12 astronauts to support Apollo applications missions, as well as having a cargo module at the rear. It was also intended to have landed using the parasail technique originally proposed for Gemini, touching down on a runway with skids derived from the X-15. Further studies investigated lunar proposals for Gemini, positing that using the existing program's hardware to land on the moon would significantly reduce the costs of the Apollo program. They proposed a Gemini-Centaur combination to perform lunar flybys, another vehicle that would have required an eyeballs-out injection burn, and lunar orbit missions performed with stacks of Agena and Centaur upper stages that would be docked to in orbit. The proposal even went so far as proposing an early, lightweight one-man lander, and I'm gonna be honest, just taking one look at that thing, absolutely not. Of course, all of these ideas were for naught, because Apollo was ready on time and had more robust hardware capable of not only doing the job, but doing it well. Gemini would unfortunately remain as a brief footnote in aerospace history, though there was one other opportunity to expand it that did, at least briefly, get off the ground: MOL. However, before we get to that, we need to talk about what inspired it. As early as World War II Germany, suborbital spaceplanes were being considered for military applications. They proposed a rocket-powered bomber capable of being fired up into space, dropping payloads over the United States, and then landing in the territory of the Empire of Japan. The German scientists picked up by the United States during Operation Paperclip, specifically Walter Dornberger, who worked with von Braun on the V2 program, tried to continue this idea, eventually ending up with what was called, at the time, Weapons System 464L. It will go down in history, however, as the Boeing X-20 Dyna-Soar, acting as a successor to the North American X-15. This rocket-launched plane would be capable not just of suborbital bombing campaigns, but of doing orbital reconnaissance and maintaining, or capturing, satellites. In 1958, 9 companies vied for the Dyna-Soar contract, and it was awarded to Boeing in the next year, while the Titan III was chosen as the launch vehicle. It would carry a single pilot at the front, equipment at the back, and an upper stage at the back that would allow for orbital maneuvers and a launch abort if necessary. A heat shield of refractory metal would protect the window during re-entry, while the entire bottom surface would be made from molybdenum. Molybdenum? I'm not sure. An extremely heat-resistant metal. The refractory heat shield would be jettisoned after the vehicle went subsonic so that the pilot could see and land it using retractable wire brush skids instead of landing legs. Dyna-Soar got far enough into development to have mock-ups built and even to have astronauts secretly chosen to fly it, one of them being Neil Armstrong, who had already flown the X-15. However, the project was also very expensive and lacked a clear goal to focus on. With NASA taking charge of manned spaceflight, it was questioned whether the Air Force should have their own manned program at all. Secretary of Defense Robert McNamara began to question whether Dyna-Soar was necessary at all, asking if Project Gemini could be just as feasible for a space-based weapon system. It was eventually found that the Air Force had put all of their emphasis on controlled re-entry while not having any real objectives for what they would do while in orbit. In 1963, the Dyna-Soar program was cancelled, and on the exact same day, the Air Force announced a new program. Oddly enough, a spin-off of Project Gemini, the Manned Orbiting Laboratory. The Air Force in the early days of space exploration really wanted a program for manned orbital reconnaissance. We'll discuss why that's silly in just a moment, but their second attempt, MOL, tried to ape off of Gemini for its design. It would use a Gemini B capsule mounted on top of a cylindrical laboratory module designed to hold a crew of 2 in a polar orbit for up to a month at a time. The Gemini module was heavily modified, the biggest addition being a circular hatch in the heat shield, allowing for passage into the laboratory. During development, MOL would compete for funding with both the Vietnam War and Skylab, but it would get far enough that ground was broken on Vandenberg Space Launch Complex 6 to permit the polar launches. Slick 6 would never see an MOL flight and sat mostly abandoned for some time before being completed for polar launches of the Space Shuttle, which were subsequently scrapped after the Challenger disaster. MOL even had its own unique training spacesuit design, as it would be needed to turn around and access the hatch to the laboratory, while normal Gemini astronauts would either remain seated or exit for an EVA via the main hatch. MOL intended to improve on existing spy satellites by having astronauts capable of surveying a target and deciding whether or not a photo was worth taking. It was found that out of 159 photos taken by KH-7 Gambit satellites, only 9% of those would show missiles on the launch pad, and out of 77 photos of missile silos, only 21% were taken when the silo doors were open. It was believed that MOL would be 45% more efficient in its use of film, as astronauts could react to cloud cover and more effectively choose targets to photograph. Moreover, the MOL could be developed further to include infrared, multispectral, and ultraviolet photography, and eventually evolve into permanent space stations, including one that could house 40 astronauts in synchronous orbit, capable of making key strategic decisions in a wartime scenario. MOL did fly once, sort of. In November 1966, a Titan III-C launched from LC-40 at Cape Canaveral, carrying an MOL mock-up built from a Titan II fuel tank, and beneath it, 2 Air Force satellites. The Gemini spacecraft on top, being the first crew-capable spacecraft to fly twice, though it didn't have crew this time, separated after the craft went suborbital, though the laboratory and satellites continued in a low orbit. Despite being a mock-up, it did contain a handful of experiments: a prototype attitude control system, a prototype hydrogen fuel cell, micrometeoroid detectors, and a few more. As MOL fought for budget allocation and to win public opinion in an array of increasing fears of nuclear weapons, it was also suffering delays in development and mounting costs. At the time, camera and satellite technology was steadily increasing. The usefulness of MOL as a crewed program was coming into serious question by the time Richard Nixon was sworn in as president, who ordered for defense spending to be cut in every possible area. By June of 1969, MOL was quickly on the chopping block, with all work ceasing and the project being officially cancelled on June 10th. Reportedly, it happened so fast that one MOL astronaut heard the news on the radio while he was driving to work. So from here on in, I really don't have much of a way to organize these things, so let's just talk about SSTOs, or single stage to orbit, beginning with the Delta Clipper. I could spend all day talking about the possible advantages and disadvantages of a single stage to orbit launch system, however, that's already been done and by better people, so let's just talk about what Delta Clipper was. Started in the early 1990s, the DCX, standing for Delta Clipper Experimental, was an uncrewed prototype for what would eventually be a reusable SSTO that both took off and landed vertically. Built by McDonnell Douglas and partially funded by NASA, it was a simple conical craft designed for re-entry and landing base first, considered the most feasible given that the engine exhaust made shielding the bottom already a necessity, and it wouldn't need to perform any kind of flip maneuver to touch down. One problem it did have was with partial involvement of the US military, who were hoping, as usual, for polar launches. If you're wondering why that's always a thing, polar orbits are ideal for spy satellites because they'll end up passing over all of the Earth at some point or another as it rotates beneath them. However, this rotation is also a problem for potential crewed spacecraft. The desired safety requirement is to be able to abort once around, meaning to re-enter and land after a single orbit. However, a single orbit taking around 90 minutes can cause the Earth to move up to 2,400 kilometers, and Delta Clipper wasn't designed with a whole lot of cross-range steering in mind. Because of this, it's possible it never would have had a crewed variant. DCX construction started in 1991, built largely from commercial off-the-shelf parts to save on costs. 2 years later, it made its first hop test, flying for 59 seconds to 150 feet, hovered, moved sideways, deployed its landing legs, and successfully touched down, marking the first time a rocket ever landed nose up. It flew 2 more successful flights, first to 300 feet then to 1,200 feet, the latter of which included a 180-degree roll to test stability. At this point, funding was shuffled around from the military to NASA, and testing resumed, with the 4th flight climbing to nearly 3,000 feet. The fifth flight was its first partial failure. A small hydrogen explosion damaged the craft during the flight, but it still managed to land safely, demonstrating successful auto-abort and landing capabilities.
Yeah, baby.
Good out of 100 feet. We got a pitch program.
Something dropped off. Fell off. Something else. Something else fell off. All four doors.
Auto land.
Yeah. Landing gear is there.
Auto land. No.
Wing up.
Can we recover?
Easy,
baby.
It's in the gypsum too, buddy.
Easy, baby. Well, we've had a failure. We don't know what's happened yet. We're down at the landing pad, the guard shack now, getting ready to go in.
The DCX would make its final flight on July 7, 1995, which cracked the aeroshell during a particularly hard landing. Lacking the funds for repairs, NASA took on the program fully and upgraded the test unit to the DCX-A, incorporating new lightweight composite materials and improvements to the control system. The first 3 flights of the DCX-A were successful, though the debut landed too slowly and caused a small fire in the aeroshell. The turnaround was fast, with 2 of its test flights occurring only 26 hours apart. It also conducted several rotation maneuvers, successfully moving from nose-first to base-first flights, showing a forward attitude re-entry was possible. However, on its final test flight, a landing strut failed and the craft toppled over, causing a rupture of the LOX tank and complete destruction of the vehicle.
Landing Q limit. Out of 3,000, heading for 2. Landing high thrust. Out of 1,000. Out of 500, 400, 300, 200.
Missing a gear.
Cell ramp down.
Where?
Landing small negative. Engine out.
She's coming over.
Okay, we had a gear that was not out. Yeah, fire suppression, there you go.
NASA, dealing with budget constraints, decided not to build a new craft, canceling the Delta Clipper in favor of development of the Lockheed Martin VentureStar. Surely this one would go well, right?
In the business, we call this foreshadowing.
The Space Dorito, oops I mean the VentureStar, was a proposed reusable launch system from Lockheed Martin intended to replace the Space Shuttle after its retirement. Instead of using external fuel tanks and boosters, VentureStar would use 7 inline aerospike engines and built-in fuel tanks, launching vertically as a single piece and returning in the same dimensions on a runway. Its simplicity would allow for it to go through much less processing, not needing to be lifted and assembled together with other components like the shuttle had been. It also planned to use a metallic thermal protection system designed to eliminate large amounts of man-hours required for servicing the thousands of ceramic tiles on the shuttle's heat shield. In the case of engine failures, all 7 of its aerospike engines would operate at a reduced thrust and could then be throttled up to compensate for a lost engine. It was also more environmentally friendly than the shuttle, ditching the hydrogen chloride produced by its boosters in favor of a purely hydrolox system that produces only water vapor. You know, I sort of skipped over how aerospike engines work, didn't I? I can't expect someone to just look at this thing and immediately understand what it is. Aerospikes are an altitude compensating engine, designed to have equal efficiency at virtually any altitude. Traditional bell nozzle engines are individually sized for different altitude optimization. In short, the bigger the bell, the higher up it'll be most efficient. Aerospikes, however, use an open nozzle shaped like a ramp or a spike, along which the exhaust gas flows, shaped by the surrounding air pressure and making it effectively self-adjusting. Lockheed Martin developed the X-33, a subscale uncrewed technology demonstrator, to try and prove the principles of VentureStar early in 1996. In 1999, the composite liquid hydrogen fuel tank failed during pressure testing on the stand, leaving NASA to conclude that the technology of the era simply wasn't up for the job. This, combined with developmental difficulties of the aerospike engines and an ideal wing shape, led to NASA withdrawing federal support in 2001. Lockheed Martin decided the project wasn't worth continuing without government support, and the X-33 was cancelled, with a fully completed launch site at Edwards AFB, a 96% complete prototype, and 0 flights. Eventually, NASA would regain crewed flight capabilities in the post-shuttle era via the SpaceX Crew Dragon, so in that case, let's talk about something SpaceX wanted to do with Dragon, but never did. Red Dragon. No, not the Thomas Harris novel or the Brett Ratner movie, the Mars Crew Dragon. Conceived in 2011, Red Dragon was a concept to use Falcon Heavy rockets to launch uncrewed Dragon 2 capsules on low-cost Mars missions, testing techniques for potential entry and landing on Mars using equipment that could be used by human crews. This was basically kind of a test run for SpaceX's current plans to colonize Mars that they announced in 2016. The original idea was to incorporate Red Dragon into NASA's Discovery program, their current deep space missions that include Lucy, Psyche, Messenger, the various Mars missions, and several others. They ended up not receiving funding as part of Discovery and would instead develop it alone, though they did sign an unfunded contract in which NASA would provide technical support. The $400 million mission would send a modified Dragon module to land on Mars using landing legs and its Super Draco retro-propulsion thrusters already used in the event of a launch abort. However, SpaceX decided to go bigger first. With the Starship program taking off, Elon Musk announced that the development of Red Dragon had ceased in favor of pursuing the big f***-off shiny rocket. Anyway, speaking of crewed missions to Mars, I guess it's time to discuss the cancellation of Constellation. Starting around 2004, Constellation aimed to first complete the International Space Station, return humans to the Moon, quote, no later than 2020, and end the program with a crewed flight to Mars. This was even reflected in the program's logo. The 3 crescent worlds on it are the Earth, the Moon, and Mars. On January 14, 2004, President George W. Bush announced the vision for space exploration intended as a way to regain public enthusiasm for spaceflight. The world had just seen the second space shuttle disaster, and it occurred largely through the same channels as the first. A lax safety culture and a compliant space agency that had gone from pushing boundaries to pushing papers. Basically, the VSE said, look at the absolute state, and put forth a plan to put things back on track. Sustained and affordable robotic programs to explore the solar system, returning humans to the Moon, and putting us on the route to finally get to Mars. The shuttle was to be replaced with a new crew vehicle, later named Orion, that could perform low-orbit missions, lunar missions, and eventually the first Mars missions. Returning to the Moon meant returning to something that hadn't flown since 1973, a super heavy lift launch vehicle. In 2004, the last time an SHLV had launched was the final Saturn V sending Skylab into orbit. So, enter Ares 5. Constellation planned to use 2 vehicles for the lunar missions. The Ares 1 would launch Orion into low Earth orbit, and Ares 5 would launch Cargo, the Earth departure stage, and the proposed Altair lunar lander, which would then rendezvous in Earth orbit. Ares 5 would repurpose hardware from the shuttle era, with one proposed configuration using the shuttle's RS-25 main engines and 2 shuttle-derived solid rocket boosters. The hope was to create a rocket as powerful as the Saturn V, but on a lower budget. We'll come back to that. NASA cited a number of reasons for returning to the Moon: extending human colonization, picking up lunar science where Apollo had left off, testing new technologies to serve future missions, promoting international research, and to re-engage the public's interest in spaceflight. Administrator Michael D. Griffin said, quote, the goal isn't just scientific exploration. It's also about extending the range of human habitat out from Earth and into the solar system as we go forward in time. In the long run, a single planet species will not survive. If we humans want to survive for hundreds of thousands or millions of years, we must ultimately populate other planets, colonize the solar system, and one day go beyond. NASA estimated the cost of their programs, both Constellation and the Commercial Crew program, to be $230 billion between 2004 and 2025. However, their inability to provide conclusive timelines that kept slipping further and further, as well as struggling to overcome design and technical challenges, cast doubt on the program. Constellation would see only one test flight in its lifetime, the first test flight of Ares 1X, a technology demonstrator for Ares 1, in 2009. Ares 1 intended to use a single solid rocket booster as its first stage, and a second stage powered by a J2X engine derived from the J2 engines used on the second and third stages of the Saturn V, though the original design called for a single RS-25, the Space Shuttle main engine. Ares 1X, however, didn't have an active second stage. It used only a 4-segment SRB with a mass simulator for the missing 5th segment, and a simulated upper stage that didn't have an engine. It was intended only to demonstrate the principles of an Ares 1 flight, carrying it through first stage flight, demonstrate the staging sequence, and the ability for the booster and capsule to land. And it did exactly that. Ares 1X was a complete success, though there was some thrust oscillation during launch that raised a few eyebrows, as well as a bit more damage to the pad than had been expected. Both pad elevators were blasted apart from exhaust, an obsolete shuttle oxidizer line was torn open, and communications lines were destroyed. While the capsule was recovered safely, the parachutes that slowed the booster before splashdown had problems, causing one to fail fully and a second to fail partially, reportedly common in space shuttle boosters. Divers noted that a lower portion of the booster's casing had buckled and its forward segment fractured. Upon taking office in 2009, President Obama declared Constellation to be, quote, over budget, behind schedule, and lacking innovation. After a review, Constellation was excluded from the 2011 federal budget, making the program officially kaput. Development of the Orion capsule was continued, and funding was allocated for development of a new heavy lift rocket, what would eventually become the Space Launch System, or SLS. However, in between these two was Direct and Jupiter. Intended as alternatives to the Ares rocket, the Direct proposal utilized a series of rockets called Jupiter. The idea was to use a common core stage between all of the rockets, as well as reuse hardware and facilities from the Shuttle program, maximizing a direct transition between the two programs, hence the name Direct. Like Ares, Jupiter rockets would utilize Shuttle SRBs between 3 and 4 shuttle engines on the core stage and RL-10 engines on the second stage. Over time, this design was altered to instead use RS-68 engines on the core stages, taking from the existing Delta IV rockets, and the J2X engines on the upper stage to incorporate the already in development work from Constellation. A third iteration returned to Space Shuttle engines, and when work on SLS was mandated in 2010, the team behind Direct declared that they had succeeded in what they wanted, and disbanded. Let's hop across the pond for a moment and discuss a few cancelled projects from Europe. First up is Blue Streak, or rather the Europa rocket. Developed by the European Launcher Development Organization, a precursor to the modern European Space Agency, Europa aimed to be the flagship launch vehicle for European satellite launches. Blue Streak was a mid-range ballistic missile intended to be a British nuclear deterrent in the 1960s. It was eventually integrated into the Europa program, intending to serve as the rocket's first stage, and was tested in Australia due to lacking an appropriate test site in the UK. However, rising costs of the program eventually led to its cancellation in 1972, and it's a real shame because you can see its iterative progress through its test flights. 2 successful first stage tests were followed with 2 failed second stage tests, after which 2 successful second stage tests ended in 2 third stage failures. On its final 2 flights, all 3 stages succeeded, but the payload failed, more specifically the payload shroud on the second to last. Bit by bit, the rocket was obviously beginning to work, but it was all for nothing. In a related vein, there was also Black Arrow, which intended to use a lot of lessons and technology from the Blue Steel missile of the 1960s. Man, Blue Steel, Blue Streak, Black Arrow, Black Knight, great naming schemes coming out of Europe around that time. Black Arrow was among the shortest rockets ever made capable of delivering a payload to orbit, compressed into a very compact form factor. It saw only 4 launches during development. On the first, a suborbital test, an electrical fault caused the engines to swing wildly back and forth. It began to roll before even clearing the launch tower, and began to disintegrate about a minute into flight. Its first stage engine failed, and was destroyed by range safety as it fell back to Earth. This was deeply concerning for project management, as the program didn't have enough funds to deal with a second failure. Thankfully, the second launch was an entirely successful suborbital test of both stages. This encouraged the program to try an all-up test with a payload, the Orba satellite. However, a leak in the oxidizer pressure system for the second stage caused it to cut out early. The third stage was left unable to reach orbit, and the rocket plummeted back to Earth. A review found no major flaws with the rocket's design, and minor modifications were made before a 4th launch successfully placed the Prospero satellite into orbit. This made the UK the 6th nation to place a satellite into orbit by their own means. The name Prospero, coming from Shakespeare's The Tempest, proved to be rather prophetic, since Prospero was a sorcerer who gave up his powers. Following the successful launch, Black Arrow was cancelled on economic grounds, the government stating it was cheaper to use American rockets for future satellite launches. Funny enough, prior to the cancellation, NASA had offered to launch British satellites for free, but withdrew this offer once the UK no longer had their own rocket. One last European project is Hermes, proposed by the French Space Agency and later picked up by ESA. First thought up in 1975, it was somewhat similar to the Dyna-Soar, but on a slightly larger scale. Intended to transport up to 3 astronauts and a 3,000 kilogram or 6,600 pound payload, it would be launched as the upper stage of the heavy lift Ariane 5 rocket with a service module at its rear. Following the Challenger disaster, Hermes experienced significant redesigns, further pushing back its progress and increasing costs along with developmental difficulties. Unfortunately, by 1992, a $4 billion bill and a partnership with Russia for space access made Hermes seem unnecessary in the eyes of the government. It was officially cancelled before anything bigger than mock-ups were built. At the end of the day, the history of European spaceflight is a whole lot of whining that things are too expensive after dumping money into them and cancelling them before any results are made. We're on the home stretch now, with just a few obscure projects left to mention on my list. Let's start with Nerva, the nuclear engine for rocket vehicle application. Nuclear thermal engines, or NTRs, no, not that NTR, first proposed in the middle 1950s, vastly improve engine efficiency by using a small nuclear reactor that creates heat through fission, which heats the fuel into a rapidly expanding superhot gas. The Nerva program was a joint effort between NASA and the Atomic Energy Commission, aiming to use NTRs for deep space missions, with a test site developed at Jackass Flats in Nevada, a prominent area for nuclear research. This site would be home to several prototypes that proved the principle, doubling the specific impulse for comparable chemical engines. During its testing period in the late 1960s, plans were drawn up to incorporate it into the Integrated Program Plan, which was the original larger program that would eventually become the Space Shuttle program. Nuclear tugs could be used to take payloads into higher orbits and into deep space, while the shuttle could be reserved for LEO crew missions. It was even suggested that Nerva could be substituted for an upper stage of the Saturn V, vastly increasing its payload capacity by around 10,000 kilograms to LEO. However, Nerva suffered from two major problems. The first was political concerns. Sadly, even today, nuclear technology is spooky, because people refuse to take the time to actually learn about it and instead soak up anti-nuclear propaganda, which, if you didn't know, is almost entirely propagated by the oil industry, not to get too deep into real-world conspiracies. Nevertheless, the perceived increased risks of nuclear engines caused Nerva to suffer from reduced support, and this, combined with NASA's 1973 budget cuts to facilitate the shuttle program, hastened its demise. Throughout the transition between President Johnson and President Nixon, Nerva would land on and hop off the chopping block repeatedly, alongside late Apollo missions, Skylab, and even Nixon's pet project, the Boeing 2707 supersonic airliner. For a brief moment in 1972, it looked like Nerva was going to survive the firing squad of post-Apollo cuts, even having congressional support at the time. However, Nixon chose to cancel it anyway, to the dismay of the around 20,000 people employed on the project. Now, let's take a step into goofier territory. Roton. Look at that thing. Just look at it. Is it a rocket? Is it a helicopter? The answer is yes. Developed by the Rotary Rocket Company in the late 1990s, Roton was intended to be a fully reusable SSTO crewed spacecraft. Yes, I said crewed. Not crude as in oil, crude as in people. People were supposed to fly in this thing. The company received initial investments of around $33 million from private investors, including writer Tom Clancy for some reason, allowing them to build a factory and test site in the Mojave Desert. A full-size atmospheric test vehicle lacking a rocket engine was developed to test the principles of flying, hovering, and landing as a helicopter. It flew 3 test flights, all with a pilot contained right here, one of whom, Brian Binney, also flew Virgin Galactic's Spaceship One. All 3 flights were successful, and Rotary began unfunded collaboration with NASA's Marshall Space Flight Center to adapt their fast-track engine for use in Roton. Unfortunately, even though $30 million had been raised for initial development, Rotary predicted needing another $120 million to continue. After failing to secure launch contracts for full-scale tests, Rotary closed its doors in 2001. There's a lot more I could say about this thing. I sort of fell into hysterics learning about it. From its rotor head being salvaged from a crashed Sikorsky helicopter for $50,000, to its crew compartment being sandwiched between the LOX and kerosene tanks, to its simulator scoring a 10 on the Cooper-Harper scale, Roton was the true definition of doing too much. I highly advise just looking it up and doing some light reading. However, we need to move on to the big finale. How do you end a video like this? Well, obviously you end it by nuking the moon. Yes, you heard me correctly. Project A-119, also known as a study of lunar research flights, had the end goal of detonating a nuclear bomb on the surface of the moon. Why? I don't know, gotta nuke something. No, but for real, there were 2 reasons. One is pure posturing. If the Soviets looked up at the moon and saw a flash of light made by an American nuclear bomb, it would demonstrate clear American superiority in the nuclear arms race. On the more legitimate side, a nuclear detonation would disturb the existing material on the moon enough that we could learn a lot about its geology and composition, albeit at a rather extreme cost. To evaluate those costs, a team was brought together to evaluate and predict the effects of the nuclear detonation, one member of which was a young Carl Sagan. Their analysis remained secret for over 45 years, but we know one thing for certain. Project A119 was overall deemed to be a bad idea. Surprising, I know. A nuclear detonation could make crewed lunar landings difficult or impossible, and this also was planned as a show of superiority over the Soviets. Furthermore, it could have fueled the militarization of space, or the worst possible scenario, the nuclear payload fails on its way to the moon and falls back to explode in Soviet territory. Overall, just not a good idea, so it was cancelled in 1959, most notably out of fear of risk to the population if anything went wrong during launch. Not surprising really, given that back in those days, rocket reliability was akin to flipping a coin. Ironically, it was revealed decades later that the Soviets had a comparable project that involved first photographing the moon's far side and eventually detonating a nuclear warhead on the surface. As usual, this is not a completely exhaustive list of space projects that have been cancelled. That video would be virtually never-ending, as NASA and other space programs have a graveyard that could rival Arlington. Spaceflight history is filled with people saying, "What if we," and the responsible administrations telling them, "No, that's stupid." I will admit some portions of making this video made me kinda sad. I intentionally didn't mention the budgets of a lot of these programs because frankly, it is depressing to see how much money was put into, for instance, Delta Clipper, only for it to be cancelled in favor of putting money into VentureStar, which was then also cancelled. At the end of the day, this is a list of things that a lot of money was wasted on. Maybe someday some of these projects can be revived or evolved into a workable state. Maybe someday we'll figure out how to conquer the stars like we were destined to. NASA in the modern era has even shown renewed interest in nuclear engines, so maybe we'll see some of those someday. Maybe we'll see an SSTO. Maybe we'll see a true successor to the space shuttle. That would be nice. As long as we never ever see Roton again.